A ground source heat pump is an electrically powered system that taps the stable residual heat stored immediately below the surface of the Earth. This heat can be turned into space heating and hot water for homes and buildings. Heat pumps work like back-to-front refrigerators. Feel the back of any fridge and it'll be warm. And this is because it moves heat from one place, its inside, to another, its back panel. Using this principle, it's therefore possible to heat a building. Put the interior of the fridge in the ground, thus cooling it down, while leaving the back panel inside, warming the building up. In this programme, we'll be taking a look at how a typical heat pump system is configured, design options, and issues to consider on site.
And here to talk us through the technology are Stephen Newman from Mighty Energy and Mike Moggeridge from Magpie Drilling. Thanks for coming in, gentlemen.
No problem.
This sounds remarkably simple. We can heat schools, offices, buildings using a large back-to-front fridge, is that right?
Absolutely. The heat pump process is a very established technology, very reliable. And yes, all you have to do is grab the energy that exists in the ground, upgrade it, and then you can heat buildings, you can heat schools, you can heat whatever you want.
You can heat and cool the school too.
So as we speak, engineers are specifying this sort of technology?
Yes.
Yes.
Yeah, increasing number.
Now, the conventional way to heat a building is to burn fossil fuel at
Yeah.
not particularly high efficiencies, 90% for a normal boiler.
Yeah.
Why does ground source energy do so much better than that?
Because when you're burning a fossil fuel, what you're doing is you're taking that fossil fuel and, as you say, you're burning it. So you can never achieve more than, say, 99% efficiency. There's a limit. With a heat pump, what you're doing is you're not creating energy. You're taking energy from where it exists at one condition and you're upgrading it to the higher condition you want. So the beauty of a heat pump is you're taking energy that already exists. When you burn a fossil fuel, you're creating energy by taking one fuel and converting it. It can never be as efficient.
Do you have to put the heat back, incidentally, afterwards?
With a ground source heat pump, you have to design the heat exchanger in such a way that if you're going to continuously draw energy from the ground, the heat exchanger must be sized that it doesn't exhaust the ground. But as Michael mentioned earlier, you can also use a heat pump for cooling. And the most efficient systems are ones that heat and cool, because then you take energy out in the winter, but you put it back in the summer.
Now, Mike, let's be sure of our terminology. We're not talking about geothermal energy, are we?
No, geothermal, or true geothermal as most people see it, is very high temperature, in excess of 100, 200 degrees Celsius. And people use that to generate electricity using steam turbines. What we're talking about is a very low grade heat, commonly between 9 and 12 degrees Celsius, that's stored within the ground. And when you change that volume of energy, when you reduce it to 6 or 0 degrees Celsius, that's when you're taking the energy from the ground and putting it into the building.
How do the costs stack up?
Costs of a ground source heat pump are higher than a boiler system if you look at initial capital cost. However, if you look at life cycle costs, then a ground source heat pump will win, especially if the energy that powers your heat pump is renewable as well. So, for example, you have a building that generates its own electricity via wind or solar, you can have a zero carbon solution. You can't do that with a boiler. And forthcoming government incentives will mean that ground source heat pumps, the cost differential is going to disappear.
So, for example, a typical suburb of any UK town or city, could the whole suburb be heated using ground source energy?
Yes. And indeed, Michael and I have worked on various projects. We're doing office blocks, we're doing colleges, we're doing houses. We are covering a typical suburb. We're covering all the property types. So it is happening.
OK, well, let's take a look at how a typical ground source heat pump system works.
There are three main components: a ground loop which collects the heat pump itself, and the building's heat distribution system. The ground loop simply comprises lengths of pipe buried in the ground, either in a borehole or a horizontal trench. The pipe is usually a closed circuit and is filled with a mixture of water and antifreeze, which the heat pump circulates, absorbing heat from the ground. The heat pump itself has three main parts: the evaporator, which takes the heat from the water in the ground loop and transfers it to a refrigerant, changing it from a liquid to a gas. The compressor, which compresses the gas, causing the temperature to rise. And the condenser, which transfers the heat from the hot gas to the central heating system. The heat distribution system can consist of underfloor heating or radiators for space heating, and where applicable, water storage for hot water supply.
Mike, let's talk about the ground loop. When would you go for a borehole, say, and when would you go for a horizontal trench?
Well, essentially it depends on how much of a footprint you have for your property. If you've got a massive school playing field and you're absolutely sure that you don't want to sell that on at a later date, then you can go for a horizontal system, which is slightly cheaper, not quite as efficient as a borehole system, but it is, there are cost savings there. However, if you've got a much larger building load and you don't want to sterilise that ground, generally boreholes are the favoured method, and those can vary from anywhere from between 50 to 200 metres deep.
So say what would a detached house require, say needing to draw 10 kilowatts of power?
10 kilowatts of power will probably come from a set of slinky trenches, somewhere in the region of 250 metres of trench. If you're looking at borehole length, you're looking at anywhere between 120 in the best case scenario to 280 to about 180 metres in a less favourable scenario.
Let me ask you about the heat pump itself. I guess, is that analogous to the squiggly bit of tubing on the back of your fridge?
Vaguely. I mean, a heat pump is a fridge working backwards, and the squiggly bit on the back of your fridge, the condenser, basically becomes the heat exchanger that heats the water, and then the evaporator is connected to the ground loop. Where there is a difference is that these days heat pump compressor technologies move forward a lot. So the quality of the machinery involved in a heat pump is much greater in a fridge, and the reliability is greater as well.
Well, continuing the analogy for a moment, is the compressor the bit that you hear on your fridge making the noise?
Yes, the compressor is the heart of the system. The rule of thumb with a heat pump system, the bigger the heat exchanger in the ground, the more efficient the heat pump. And with compressors, ideally you want an inverter-driven compressor, which will give you the most efficiency across a year.
And this condenser, I can't quite understand or comprehend how you can take heat at 12 degrees C and transfer it into enough heat to heat a building. I guess the compressor does that.
Compressor's doing that. What the compressor's doing, you're taking the water from the ground is going through the evaporator. As it goes through, it's basically causing the gas in there to evaporate. That gas evaporates, becomes a low-pressure gas. That low-pressure gas gets sucked into the compressor. And what the electricity does is drive the compressor, and the compressor basically pounds that gas, makes it a very high temperature, high pressure fluid. So when it gets to the condenser, it wants to give up its heat. So by cooling it with water, you basically transfer the heat from the refrigerant to the water, and then you have an expansion valve which allows the gas to expand and cool down again, so the whole process can start.
If you imagine a bicycle pump, when you're pumping up your tyres and you're making a lot of pressure and that gets very hot, you've got heat, and essentially that's part of it's friction, but most of it is because you're compressing the gas.
So you're putting your finger on the end, compressing the little tube, and it gets warmer.
Yeah, exactly.
And then conversely, when you push your finger in to the valve and let the air out, after a while you get a cooling effect because it's expanding.
So is it possible to heat a building to sort of, the sort of temperatures that people these days are used to?
Yes, no problem
Absolutely.
at all. Up until recently, the challenge was not the heating of the building, it was the domestic hot water. Because you can heat a building with water at 30 degrees if you use underfloor heating. The problem has always been the domestic hot water. But now with modern compressor technology, we can heat water to 65 degrees, which is what you need. So that's been the major advance. And what the ground source heat pump does means that across the year you get a higher efficiency than any other solution.
Okay, well, let's have some look at some design options.
There are three main options when it comes to installing a closed-loop ground source heat pump system. The first is vertically in a borehole as a series of long U-shapes in well holes. Depending on energy needs, boreholes are usually 50 to 200 metres in depth. Alternatively, piping can be installed horizontally in a trench about 1 to 2 metres deep, or even a body of water. Trenches cost less than a borehole, but need more land area. Spiral, horizontal or slinky coil piping can also be used. This needs a trench of about 10 metres length to provide about 1 kilowatt of heating load. In an open loop system, the ground loop pumps water from a well or other source of water. Open loop systems using groundwater are usually more efficient than closed systems because they're much more closely matched with ground temperatures.
Okay, Mike, let's talk about the borehole option. How deep, what sort of spacing?
It's entirely dependent on two things. Number one is the thermal loads on the building, that's heating and cooling loads that you're looking for the ground to generate. The second is the ground conditions themselves. Now, what you'll find is effectively you're looking at a volume of ground that you want to interact with. So if you have very high conductivity deposits that will offer a lot of energy very cheaply, then you'll probably want to space your boreholes quite a way apart, but you want to sit the boreholes within that area. But if you've got, for example, in London, where you've got London clay, which is low conductivity material, you probably want to penetrate that and go on down into the chalk, which has got a lot better conductivity, and extend your boreholes deeper in that. And in London, we're drilling up to 200 metres to tap that source. But effectively, what you're doing is you're taking a volume of ground and you're putting a heat exchanger in it, which is the boreholes, and then that essentially draws the energy into it in the form of heat, or pushes it away in the form of when you do cooling.
Let me just pick you up there about ground conditions. You cited the example of London clay. You go to 200 metres possibly. What would you do, say, in a silty sandy gravel? What would you do there?
In a silty sandy gravel, basically it depends how deep it is. That would commonly be closer to surface. If it's dry, then you've got very poor conductivities because the air effectively acts as an insulator. But if you've got it very wet, and the water is one of the best conductors of heat you can get, you will find that will be an incredibly efficient system.
So groundwater levels play an important part too. What sort of trench size would be needed, moving on from boreholes, for, say, our average size detached house again?
You're looking around about 200, 250 metres, but it all depends on what kind of ground conditions you're encountering. There's some types of ground that will give lots of energy very freely, very quickly, and there's others that will give a lot less and are a little. You need to encourage it a little more.
What about spiral piping? When would you use this slinky coil stuff?
Well, it's one of those things. It's not a personal favourite of mine. It's one of those installations. If it's more the DIY market, a very low cost, low end solution. It's not highly efficient. So it's something that you would use if cost is a limiting factor. If the ground is easy to excavate, then you maybe look at it. But it's more of a very peripheral option, I would say.
So possibly for someone's back garden where space is limited.
So
A good size back garden.
you need a good size back. That's the thing. You need a lot of space to make it work, really. The thing that affects it is that because it's quite close to the surface, it experiences a lot of ground temperature change. So we tend to prefer doing vertical systems.
We haven't talked too much about open loop systems. When would you go for that particular design option?
Basically, open loop systems are where you're extracting groundwater, and it's exactly as you do from a borehole for drinking water, for example. You extract groundwater from one borehole, put it through a heat exchanger, and then dump it down another borehole. So you have two boreholes. Now, these are incredibly efficient systems, but pulling together an open loop borehole is a lot more expensive. So you're looking at a much larger system. I would suggest somewhere between 200, 250 kilowatts is the minimum limit you want to look at. However, there are a lot of schemes that have been installed, and we've done some ourselves that deliver in excess of 2 megawatts of heating and cooling throughout the year. So they offer much greater efficiencies, and they're more for where you've got. They're very popular in London, where you've got minimum footprint. You've got two sides of a building. You put one borehole on one side, one borehole on the other, and you can deliver an awful lot of energy using that system.
And presumably, from a low carbon point of view, an open loop system is a very, very good idea.
Absolutely. Beauty of an open loop system is that the medium you've got, the water, is between 12 and 14 degrees. If you've got a building or a process that requires a lot of cooling, that water at 12 to 14 degrees can be used as the primary cooling medium, and you then don't need to run a compressor, so you're saving a huge amount of energy. And there are risks associated with open loop systems. You have to make sure that the wells are going to work and that you've got the right legislative compliance in place. But as long as it's designed properly, it's a very good system.
It occurs to me that if you're engineering any ground source heat pump system, the site conditions are fully appraised. For example, if you're next to a body of water, or you can create a body of water, that's got to be taken into account in the design stage.
That's exactly right. Essentially, when you look at any ground source system, or if you're considering any renewable technologies, you need to do a feasibility study at the very earliest stage. And that's probably before you do any detailed design within the building, because then the ground source heat pump system works the most effectively when you've got, for example, underfloor heating. So you need that to be included very early on within your building design. And then when you decide, yes, I want to use a ground source system, you then need to look at, is open loop feasible? Have I got enough load? Have I got water on underground? Have I got a pond or a body of water nearby I can tap into? Or is it going to be a closed loop? And if it is closed loop, what sort of conductivities am I going to be getting from the ground?
Okay, well, let's have a look at a case study. Let's imagine that we're going to install a closed loop system in a new building. What are the main issues that have to be taken into consideration?
First of all, there needs to be adequate investigation of site geology and ground conditions. Is there a ground investigation report and groundwater information? Has a test borehole been sunk? Has proper design information been provided? For a closed loop system, for example, has depth, diameter and spacing been specified? For the installation, what is the loop diameter required, plastic grade and strength and backfill specification? And what sort of quality assurance will be put in place for the scheme?
Like any construction project, we need a site investigation report. What sort of information are you looking for in that report?
Basically, I need to understand what the underlying conditions are going to be, and that's going to be superficial deposits, the unconsolidated stuff, the made ground, whether there's terrace gravels or anything like that. Then I need to understand what the geology is below that, the solid geology, whether it's going to be clay, lower green sands, hard limestones, or whatever it might be. Once I've got that information, I can then decide on exactly how I'm going to drill it and what the most efficient method is. And then I also need to know what spacings between the boreholes I'm going to have to drill and what kind of installation we're going to be putting in.
Are there any particular challenges from made ground? Most projects would these days take place on previously engineered ground.
The big, not particularly. The kind of equipment we use is very modern and we can cope with most ground conditions. The main thing with made ground is contamination, and we're always very specific that we anticipate materials when we drill.
And groundwater information.
Groundwater information in some cases is very useful. That's more of a design thing than a drilling side of things. Although we may decide on a certain site, if there is no groundwater at all, the ground is very hard, we may decide to do something called air hammer drilling, which is very fast, but if there was groundwater there, it would make a hell of a mess. But
would you install piezometers in advance, say, so you knew what the conditions were?
No, you could glean that from regional records, Environment Agency records, BGS records, etc.
What about design information?
Well, the most important thing for us on the ground source heat pump, on the heat pump side, which is where I get involved, is understanding the building loads. What we need is to understand how the building needs to be heated, how the building needs to be cooled. We're looking to create a solution where the heating and cooling loads are as balanced as possible, because the better the balance on the system, the better the balance in the ground. And effectively the efficiency of a ground source heat pump is a factor of getting the difference between the ground temperature and the delivered temperature as small as possible. So we want to make everything work together as a system, and we want to see a nice balanced load. It's the key thing for us.
What sort of QA would you see in place during a typical project?
It's pretty comprehensive, to be honest, on a closed loop system especially. Basically, if you imagine you've got a driller who's come to site and he's just told you, I've drilled a borehole to 100 metres and the loop has gone to the bottom of that hole, I promise. What I would do myself, or what we do as a company, is we demonstrate by either dipping the borehole or by using loops that have a depth increment on there. You then need to make sure that the loop has no holes in it at all, so you do something called an air pressure test. And then once that's complete, you want to make sure there's no blockages in your loop at all, and you flush water through to demonstrate that there's no there's no blockages. Then essentially, once you've completed that, you want to seal your system, put a bier wash through it and a bier side to keep it nice and clean, and it doesn't get have foul water and get stuffed up like that.
Where it's best to use ground source energy using the heat pump system? At home, offices, schools? What sort of scheme lends itself to this particular technology?
Residential market, no problem at all. Norway, Sweden, Denmark, it's been done for years, and America, Canada in particular. Commercial ground source heat pumps, Michael and I are working on a scheme at the moment which is 2 megawatts capacity. It's very, very large. Effectively, the application is it's almost limitless. There aren't many things you can't do with a ground source heat pump. The best applications will be ones where you can achieve the highest level of efficiency. And that's going to be an application where you're doing heating and cooling. So large commercial projects will give you the most efficient solution.
Because it seems to me that in the home, heating your own home, for example, you've still got to consider you need to electricity to power the heat pump in the first place, and there's a balancing act to be done there.
There is, but using electricity to drive a heat pump is much less carbon intensive than using gas to drive a boiler. And I think going forward into the future, as we become a country that's more and more reliant on gas imports, going towards a residential market that's heated by electricity will give us a lot more options going forward into the future.
So how do you see things developing in the future, Mike?
As a company, we're very buoyant. We're striking some key partnerships at the minute. Mighty is one of the key ones that we've got. But essentially our turnover has gone from, we started at the end of 2006 and saw ground source as an emerging market that we wanted to get involved with, and we've now developed that. We're probably the leading ground source drilling company in the country. We're very busy at the moment, and we only see it getting busier as we go further into down the road. And when you look at government incentives, it's not legislation yet, but what they're looking at is something called the renewable heat incentive, whereby if you use a ground source heat pump, effectively you're paid 9p per kilowatt hour by the government, or as a rebate for every kilowatt hour you produce. And that's set to come in 2011. And when that happens, I think the whole industry will explode and go very, very, the growth will be immense.
So ground source energy very much on the up.
Absolutely, absolutely.
I'm afraid, gentlemen, we're out of time. Many thanks for coming into the studio for sharing your thoughts with us today. Don't forget, there's more in the study notes. Don't forget to take a look there. But for now, from all of us in the studio, goodbye.